relationships between the applied loads, shear forces, and bending moments, which will help us better understand what our diagram should look like. Let's consider a beam loaded by an arbitrary distributed force. We can zoom in to look at an infinitesimally small segment of the beam with a width equal to dx and draw the free body diagram. Over such a short section of the beam, the distributed force can be assumed to be uniform, and we can replace it with an equivalent concentrated force. By applying the equilibrium equations to this free body diagram, it is possible to demonstrate that the following relationships exist between the applied distributed force, the shear force graph, and the bending moment graph. The quantity dV over dx is the slope of the shear force curve, and at a given point along the beam it is equal to minus the distributed force. Similarly, dm over dx is the slope of the bending moment curve, and at a given point it is equal to the shear force. If we integrate the first equation, we can show that the change in shear force between 2 points is equal to the area under the loading diagram between those 2 points. And if we integrate the second equation, we can show that the change in bending moment between 2 points is equal to the area under the shear force curve. This is really useful information we can use to help construct or sense check our shear force and bending moment diagrams. Let's take a look at an example. This beam has an applied distributed force and a concentrated force. Let's quickly draw the shear force and bending moment diagrams. By using the free body diagram method, we can show that the bending moment curve for the section of the beam under the distributed force is defined by the quadratic equation negative 4x squared plus 34x plus 68. If we differentiate this equation, we get negative 8x plus 34, which based on the dm over dx equation above, we now know is the equation for the shear force curve in this section of the beam. If we differentiate again, we get negative 8, which is the equation for the distributed force. This is a great way to sense check your shear force and bending moment diagrams. Another way of checking your diagrams is using the area equations I mentioned earlier. The area under the shear force curve, highlighted here, is equal to 34 times 2, which is 68. This is equal to the change in bending moment over this section of the beam. We can also calculate the area under the shear force diagram for the beam section under the distributed force. The total area of this section is equal to 72.3 minus 12.3, which is 60. This is equal to the change in bending moment of 60 kilonewton meters over this section of the beam. Where concentrated forces are applied, there is a sudden jump in the shear force diagram, and where concentrated moments are applied, there is a sudden jump in the bending moment diagram. These equations will not be applicable across discontinuities in the diagrams. One final observation we can make based on these equations is that when the shear force is equal to 0, the bending moment curve will be at a local minimum or maximum. Let's look at one last example. Here we have a cantilever with an applied concentrated moment of 120 kilonewton meters and a distributed force of 6 kilonewtons per meter. Again, we start by drawing the free body diagram. Because the support is fully fixed, we have vertical and horizontal reaction forces, Ra and Ha, and reaction moment, Ma. Let's look at our first equilibrium equation. The sum of forces in the vertical direction is equal to 0. In this case, the only forces acting in the vertical direction are the reaction force Ra and the distributed force. So Ra is equal to 6 times 3, which is 18. Ha is the only force in the horizontal direction, so it must be equal to 0. Next, we can take the sum of the moments acting at point A. In calculating the moment caused by a uniformly distributed force, you can remember that it is equal to a concentrated force located in the middle point of the load. This gives us Ma equals 21. To calculate our shear forces and bending moments, we will start on the left side of the beam and move towards the right. This is our first free body diagram. The shear force calculation is easy, as we only need to consider the reaction force of 18 kilonewtons. The bending moment needs to take into account the reaction moment and the reaction force. At x equals 0, the bending moment is equal to the reaction moment of 21 kilonewton meters. As we move to the right, we also need to consider the moment caused by the 18 kilonewton reaction force. This gives us the equation for a straight line. We can then move our cut to the right of the concentrated moment. The moment won't affect the shear force, which will remain constant at 18 kilonewton until we reach the distributed force. But it does cause the bending moment to suddenly drop by 120 kilonewton meters. After the drop, the bending moment is again defined by a straight line. Things get a little more tricky when we reach the distributed force. We can replace the uniformly distributed force by an equivalent concentrated force with a magnitude of 6 multiplied by the length x over which the force is applied. This force is located at a distance of x over 2 from our cut. We can then calculate the shear force and bending moment equations using the normal approach. The bending moment in this section of the beam is defined by a quadratic equation. No loads are acting on the small 1 meter section to the right of the distributed force, so shear forces and bending moments in that section will be equal to 0. Although we can't calculate displacements from these diagrams, we can use the bending moment information to predict the deformed shape of the beam. Where the bending moment is positive, the beam will be sagging, and where it is negative, it will be hogging. Where the bending moment is 0, the beam will be straight. That will give us a deformed shape that looks something like this.